Maybe. You watch, I'm gonna click submit, and then 2 seconds after I click this button, he'll show up. No, it didn't work. That usually works. Oh, those 3 seconds. I knew it. I knew it. Every time. As soon as I submit the attendance, then somebody chimes back in. All right. Life is moving fast, folks. Good morning, everybody. I don't have anyone in person here now, so please go ahead and turn on your cameras so I have some faces to see and actually talk to you. Your Zoom is broken. Well, you made it here now. Can you still hear me at least and see my screen? Yeah, it's your mic. Oh, that's fine. Today is going to be a more lecture-y kind of day. So if you do have questions, you can just type them in the chat. That works just fine. I changed it. You're not absent. All right. Today we are talking about increasing and decreasing still. We've been looking at the graph of a function and being able to identify where it is increasing, where it is decreasing, where's the maximum, where's the minimum. And that's all well and good, except you're not always going to have the graph. You can make one, but often that's going to take more time, and it's going to give you a good representation. But if the graph is not already like labeled and done for you, you're still going to want to calculate, wait, where is that point? It goes to about, is it 3? Is it more like 3.5? I can't quite tell, right? Graphs are inherently less accurate by themselves. So we want to know how you could take an equation, for example, this guy, f of x is negative 2x to the 4th minus 6x cubed plus 5x plus 2. Where is that increasing and decreasing? How are we going to be able to tell? Because that would be really useful if we could just sort this thing. Okay, it's between here and here, it's going up. Between here and here, it's going down. Say this is some analysis of stock trends or profits for the year or whatever. And you want to know, okay, when were we doing good? When were we doing bad? Okay, this has some real world application here. Now, because we're in pre-calculus, I bet you can guess what goes in this first blank. The best answer, the best way to get to what we're after is, of course, going to be calculus. We don't have calculus yet. That comes next year. We're getting ready for it. So I want you to see the difference it's going to make between having those tools and not having them. There's limitations here and now with pure algebra. Okay. Now when I say best answer, the best answer requires calculus, I'm really meaning the most accurate, in a sense, again, compared to just looking at it on the graph. And a calculatable answer. Again, not on the graph, right? We could still go graphically, and we will use that. But for right now, we're talking, what's the way that we can compute this by hand without relying on the machine to just do it? Because we also kind of want to know how is a machine figuring this out behind the scenes. Well, it's probably using calculus, but the calculus builds up on these principles. And the principle is this. First and foremost, even with calculus, we have no way to calculate those regions. There isn't a way to do it. I'll just be honest with you. You cannot say, here's the equation, and it just finds the increasing region. Because that's not a thing. Right? Regions are not a standalone item that you can compute. The only thing you can calculate are points. Okay? That's the only thing you can find on the function. Right? We know how to do that in algebra. You can plug in values of x and get values of the function back out. You can get points. In fact, the function is made up of an infinite number of points. Here is f at x equals 1. Here is f at x equals 1.1. Here is f at x equals 1.01. Here is f at x equals 1.001. Right? All of those infinite, tiny, infinitesimal decimals along the number line the function is defined for. Which means the function, as you kind of learned in geometry, a line is nothing but a series of an infinite number of points. And a point is a specific place in space. That's the only thing we can actually find. And so we define a region, right? This is actually just between two points. That's how we're going to define it, that's how we'll find it, and that's how we'll report our answer in the end anyways. You can't just say, well, it's increasing on the left side. Which, I mean, I can differentiate left from right, but where is the crossover? Where's the middle? On the left side of the y-axis? Is it always perfectly symmetrical there at the origin? No, please, that's not going to happen. So where does the left side become the right side? What if you're dealing with a cubic or higher? Or we started with quartic. That's got 4 sides to it, right? Which one's going up, which one's going down? Where do you switch? It switches at those points. What kind of points? Special points, not just anywhere on the graph. We've seen we've seen 2 of these before. We've already started talking about them. Maximums and minimums. Right? Those are easy, sometimes called extrema or extrema, the extreme points, relatively speaking. Right? And then the third one that we haven't seen before, sometimes called a POI, a point of inflection. And this is a very special kind of point that is not going to concern us yet, because it doesn't affect increasing or decreasing. This is a point where, let me draw a quick sketch here. Let's say you've got something, I mean, you could just go with the basic tangent function here. There is a point somewhere in the middle about there where we can see something changed, right? You can kind of notice it graphically, that something is different about the curve on this side versus the curve on that side. It's not a straight line, right? It was bent this way, and now it's bent that way, right? The bend has switched, but it's still increasing, right? So because it's still increasing, this doesn't change whether it's increasing or decreasing, but this is still a noteworthy type of point that we will want to remember later on. But those are the 3 main types of special points that you can have on any function on the graph there. And so we'll be mainly concerned with these two because they change where it's increasing or decreasing, right? Our curve goes up, 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 and up, and then suddenly stops. And, oh, I didn't want to actually do that. I want to keep drawing. Goes up, stops, and turns and comes back down. And so we get that point right there at the tippy top where it's no longer increasing. Now it starts falling. That's a maximum this point. It's the extreme point relative to this region. Whether or not the rest of the graph goes off and goes higher or lower, doesn't matter. So that's the thing we'll be focusing on. We need to be able to find these points to then specify the region. The region of increasing will be either between two extrema or between an extrema and infinity. Right? If we're talking about the last section on either side. So that's not going to be enough. We're going to need a few more pieces of information. We can use those points, those maximums and minimums. We're going to need the leading, not the leading coefficient really, just its sign. So whether the function starts off positive or negative, leading, of course, referring to the first term, if it's in standard form, the term with the highest power. And speaking of power, we want to know the overall power of the polynomial. And that will let us know how many points we need to find, how many sections of increasing and decreasing there will be. Okay? So let's look at that example. I've already run this function into Desmos and graphed it. So this is an approximation of the maximums and minimums. But I want to show you an example of what we can do with just this information, the function itself, the maximums and the minimums. And please feel free to stop me at any point. Let me know in chat or over voice if you need me to go back to something on screen so you can write it down. All right, I have my 3 points. And of course, I'm looking for 3 points because this was a power of 4, right? Power is 4, which means we have at most 3 extrema, maximums, or mins, turning points, if you will. We also know that because 4 is even, the ends are the same. We know this is either going to go up and up on both ends or down and down on both ends, except those are just parabolas, so let's be a little more accurate in our sketch here. It's going to be up and maybe do like a W. And so we have 1, 2, 3 turns, or start down and be more of an M. 1, 2, 3 turns. Right, whatever the power is, 1 less than that is the maximum number of extrema. I say maximum, it could be less. But in this case, I already have them listed here. We know there are 3 of them. There they are. I know the ends are supposed to be the same. This is where the sign is going to come in. In front of that leading term is a negative sign. So the negative sign most directly tells us when x gets very, very large, the whole function will be negative. So on this side, right, the positive x-axis, it will be negative. So we're looking at the second option. This is approximately what our graph is going to look like, some variation of m there. Which means we know that the first section, the first region, will be increasing from left to right. It's going up. And then after that first extrema, it'll be decreasing, and then increasing, and then decreasing. So we could, let's highlight the increasing sections here in blue, and we'll highlight the decreasing ones in red. So we can answer it is increasing from negative infinity up to whatever that first extrema is. So we'll go with the most negative x term on my list here. That would be this guy, negative 2.11. Parenthesis, I am not increasing at that point, because at that point the function is flat. It is not increasing nor decreasing. And then my second region will start at the second extrema, the minimum there. So we'll use that x value, negative 0.619. And that will travel all the way up to the third point, so up to 0.479. That is where the function increases. And then it decreases between those same set of points. So between the first point, negative 2.11, and the second point, negative 0.619. And then it decreases again after the third point from 0.479 all the way to positive infinity, but not quite reaching it. Parentheses instead of square bracket. All right, there you have, that's your final answer. That answers the question, where is this increasing? You need to find the extrema and then use the sign and power of the function to determine which side you're starting on, and then it's going to effectively alternate between each one. Any questions so far? No? All right. The next question that would come up is, oh, that's well and good, but without graphing. Actually, no, hang on, before that, let me go ahead and switch over to Desmos and show you that graph. So we can compare and sort of check our work here, right? So I've got the function input there. I don't get my little laser pointer anymore. But we have the function on the left, and then the graph. You can see I've gone ahead and highlighted each of those extrema. They also have the y-intercept point is listed there as well. I don't really need that right now. That's where I got those terms, as well as these zeros aren't coming into play. It's just those three extra points. And so from the graph, now we can say, oh yeah, easily, that's where it's increasing up to that point, decreasing down. But just having that knowledge of how a polynomial works in terms of sign and degree gives you a quick enough sketch to know which piece is going to be increasing, decreasing, and it's going to just alternate in between there. But you have to know those points, right? I could not have done this without Desmos telling me, hey, this maximum is at x equals negative 2.11. I'm not concerned about the y value for it at this point. But I can't do that without knowing these points already. And so the challenge comes in being able to find those points. We can do that for a quadratic. Okay? We know how to find the extrema, well, the extreme, what's the singular term from extrema? The extreme point, right? Because that's just the vertex. The extrema of the quadratic is the one and only vertex. And so that one we can calculate. Find where this function, x squared, is our highest power. The degree is 2. It's a quadratic. It's a parabola. Where is it increasing and decreasing? Well, quick sketch, parabolas look like this or that. I can see from the sign here is positive. So on the right-hand side, it's going to be going up. So that would be this one here. So we can ditch that. Here's our quick sketch. I just need to find this vertex point here, and that's going to change it from decreasing on this side to increasing on that side. All right. So let's solve that real quick. We've got our formula for the vertex x is equal to, it's that half the quadratic formula, opposite b over 2a. Don't need that square root part. That's just when you're actually getting the zeros. So our b term here is 6. Want the opposite of that, divided by 2 times a, which is 1. So we have negative 6 divided by 2, negative 3. Put that into the function. G of negative 3 is negative 3 squared plus 6 times negative 3 plus 9. Gives us negative 3 squared is 9. 3 times 6 is 18, negative 18 plus 9. Oh, hey, that's a 0. Look at that. So the vertex is on the point negative 3, 0. So that's the change. Really, we just need the x value. This part, I suppose, because I didn't even need to do that work. That was technically optional. All you need to know is the regions from where it's increasing and decreasing. Right? It is going to be increasing from negative 3 to infinity and decreasing from negative infinity up to but not including the negative 3. That's it. I like going ahead and calculating this, get an actual point on the graph. More helpful for understanding, but not doesn't contribute directly to answering this and only this question. Very rarely are you only answering this question. There's often more to it. All right, questions on that process? Again, this is easy with quadratics, right? You've done this in Algebra 2, find the vertex of a parabola. Straightforward. we don't have the tools yet to find the extrema of a higher degree polynomial. That's where the calculus is going to come in. Right? I looked this up. I double checked. I'm like, okay, is there any way you can do it? Not without either a graphing tool to calculate it for you or calculus. So just a bit of practice here today on quadratics. Go ahead and try that one. Tell me where h is increasing and decreasing. And since we're only dealing with plain old parentheses, numbers, and commas, you can actually type your answer into the Zoom chat, and I can see how you did. Give that a test there. All right, I've got 2 answers in. Alex, it looks like you just gave me the vertex. Can you specify which side it's increasing, which side it's decreasing? Okay, I've got 3 answers in. Good so far. We've got mostly consensus. I see a disagreement on the sign, though. Okay, most folks are saying negative 2.5. Let's double check. Let's see, my vertex is opposite of b over 2a. I should have negative of 5 divided by 2. A is a negative 1. So there are two signs here. Negative 5 divided by negative 2 is positive 5/2, or 2.5. Your vertex should be at positive 2.5, which means your cutoff between increasing and decreasing should be positive 2.5. So good job, manual G. The rest of you missed that sign. All right, and because it is starting off negative, it's going to be a upside down parabola here at 2.5, so it's going to start off increasing from negative infinity to 2.5, and then decrease from 2.5 onward to positive infinity. So let's see, so compare your answer, right? So some people got the sign switched, some people got the increase, decrease switched, probably because you also missed the sign there. And if that's a screen error and you couldn't see that, I apologize. I should have probably zoomed in on the function a little better. But there you go. Right. So that's all we can really do with this for today. As I said, we're going to need actual calculus tools to do anything for a higher level polynomial. Other equations like sine and cosine, you could actually find, just because of their cyclical nature. Once you know the amplitude and the period, you can actually determine all of those peaks and troughs. That's relatively straightforward, but we'll save that for later when we talk specifically about some trig functions. All right, so that's going to do it for us today. The rest of your class assignment then on Google Classroom, I would like for you to... Oh, no wonder nobody was watching. I didn't hit the final post button. I'm sorry. All right. Anyways, go ahead and write up just a short paragraph, a few sentences, whatever it takes. But I want you to write in words a description of what is this process that you have to put together to determine where a function is increasing and decreasing. All right? I said we would take a quiz. I guess not. I'll save that. Maybe we'll do the quizzes tomorrow. Changed my mind. Unless you want to do a quizzes right now. When does this end? 35? We got 10 minutes. That's a little short notice. I don't have it queued up. We'll save it for tomorrow. We'll be fine. All right. Any questions on what I want you to do on that actual Google Classroom post? No? All right then. Tomorrow we're continuing in with basically the same topic, but focusing more on the max and min side rather than the increasing, decreasing side. But as we saw today, they kind of go together. So I'll have a worksheet and then a quizzes tomorrow, and then we'll do something completely different. Not completely, but fairly different on Friday. All right?